In the previous video, I gave you a short catalog of the different forces we will see in the course. We learned that a force is not just a push or a pull, but an interaction between two objects or between an object and its environment. A force is a vector quantity with a magnitude and a direction. And since it has a magnitude, you might be wondering, well, how do we measure its strength, its size? What are the SI units of force? Well, the SI unit of force is the Newton, which we abbreviate with a capital N. 1 Newton of force is the force that causes 1 kilogram mass to be accelerated to 1 meter per second squared. So mathematically, 1 kilogram times 1 meter per second squared, which is a kilogram times a meter per second squared, is equivalent to 1 Newton. Now, the Newton, by the way, is what we call a derived unit, which is consisting of the fundamental units of kilograms, meters, and seconds that we talked about back in Chapter 1. To give you an idea of what 1 Newton of force feels like, go grab a medium-sized apple and just hold it in your hand. Well, the weight of that apple is roughly about 1 Newton of force. Now, typically in the United States or North America, we know about the pound as the unit of force. And so it's a good idea to kind of at least relate it to what a Newton is. And 1 pound is equivalent to about 4.45 newtons. So if you had 1 Newton, that's maybe a quarter pound roughly. Or a 110-pound person, that weight of that person is approximately 500 newtons. Over here on the left side, you can see a spring scale, and that's very typical that you'll see in old markets. A spring scale consists of basically a coiled spring in here. You can see there's a little spring in here. It's usually protected in some kind of tube. And there's a little pointer here in the middle that tells you what the size of that force is. It can be calibrated in newtons, or sometimes it'll be also calibrated in terms of mass and grams. And you also have not only spring scales, but you have spring balances, or even electronic balances that you've hopefully seen as well. I'll show you a few in class. Down below here, you'll see that we have, I have a section here saying resultant force. Well, you see, on an object, it's not typical that we just have one single force acting on it, but we have a lot of forces acting on it. And so we usually find what is called the vector sum of all the forces acting on the object, which we call the resultant force or the net force. So the abbreviation for this resultant force you could write as F net. I personally prefer to write it as using the summation sign, sum, and then F. This means the sum of all the forces F here. So when you add up all the forces, in this case there's only two forces, force 1 and force 2, the resultant force, or net force, is written as sum of F. When you have two or more forces acting at the same point, we call that a concurrent, or these set of forces, concurrent forces. So let's say I have, there's the floor here, and I put some object like this box, and then there's a rope attached to it that I'm pulling here with the tension. We have the weight pulling it down, the force of gravity. We have the normal force pushing upwards, and maybe we even have some friction opposing right along that rough surface over here. Now, in situations like this, we will often resolve our forces along our x and y axes. We'll take this tension, for example, and we'll break that up into an x component, t sub x, and a y component, t sub y. And then when we proceed into our problem solving, we'll be looking at the sum of the forces along the x-axis, and we'll also be looking at the sum of the forces along the y-axis. So along the x-axis, we would have tension here and the friction. But then along the y-axis, the sum of those forces will be the normal force, the tension in the y-axis, and the force of gravity. So essentially what we've done is we've taken this one force, tension, and broken it up into components that are along our axes. Oh, I guess I should have showed you what the direction of our axes are. So it's typical in our problems to show a little coordinate system, and we normally pick y being up and x being positive to the right. But not always. Let's say you have a box that's being pulled up a ramp. In this case, it would be more convenient not to pick an x and y axes that are along the horizontal and vertical of your page, but to tilt it along the surface that you have. So here we'll be looking for the net force that is parallel to the surface and perpendicular to the surface. And then remember that any force can be resolved along its x and y axes that you choose. So we could rewrite that as t sub x here and t sub y. So we've broken up this tension into two components along our chosen horizontal and vertical axes that are along the plane of this ramp. So obviously, hopefully you can see that if you know the tension and the angle, you should be able to calculate the x component and the y component mathematically, as we learned back in chapter 1. Okay, well the next step is to learn Newton's 3 fundamental laws of motion.